All right. I'm going to be throwing a lot of if-then statements at you here today. Let me actually hand you the notes so you have somewhere to write this down. That'd be a good idea. That would be helpful. All right. In a plane, a line is tangent to a circle if and only if. So this statement is a biconditional statement, which means that it's two different if-then statements wrapped into one here. If and only if the line is perpendicular to the radius of the circle at its endpoint. So that means we can solve these problems in two directions here, in two different directions. We can solve it in the direction of if we have a tangent, then we have perpendicular to the radius. So if I know this line is a tangent line, then that's going to give me a right angle. And the main type of problem that we're actually going to solve is we're going to draw another segment out to the tangent and create a right triangle and some Pythagorean theorem going on. That's what you're going to see most of the time on these problems. You're going to see Pythagorean theorem happen. So we can move in the direction of if we know tangent, then we know right angle. Or we can move the other way. Conversely, using the converse, if we can show perpendicular to this radius, then we're going to have a tangent. So we can figure out if a line is tangent by figuring out if we can prove and have a right angle. So let's take a look at how some of these problems are going to look here. First one, is DE tangent to circle C? This is another way of asking by the theorem I just showed. We have tangent if we have perpendicular to the radius. So my radius here is C to D. So in other words, I want this D to E to be perpendicular. So what I'm asking is DE perpendicular to CD? Is what I'm really asking here. And what we can do to show right angle, as we talked about back when we talked about Pythagorean theorem, the way we can show right angle and right triangle is by showing that Pythagorean theorem works out. Remember that we could compare c squared with a squared plus b squared, and if they matched up, then we have a right triangle. If it was less, then it was acute. If it was greater, it was obtuse. But this c squared comparing with a squared plus b squared will tell me whether we have a right triangle or not. There's an issue here. Right now, I want this to be my right angle, which means I want C to E, this distance to be my hypotenuse. But right now, that looks like it's 2, which can't be my hypotenuse. C is supposed to be my longest side. Well, that is because there's something else that we're not taking into account. 2 is this outside distance right here. That is what is 2, not the entire side length. So we will need to factor in and get the entire side length, and we'll get that through figuring out what this distance is. Good news, we already know what that distance is. That distance goes from the center here to a point on the circle here. Well, if it goes from the center to a point on the circle, then it's a radius by definition. And by definition, any radius is the same length as any other radius. That's what a circle is. That's what a radius is. It's guaranteeing that that distance from the center out to any point on the circle is going to be the same. And so what is the radius of the circle? There's another radius somewhere else. And so it's going to match it. It's going to match this radius here, which is 3. So that radius right there is 3. This outer piece over here is 2. So the entire thing is going to be 5. So 5 squared goes on the left side. And then on the right side, we're going to use my legs that build what I am claiming is the right angle. And let's test this out. 3 squared is 9. 4 squared is 16. And 5 squared is 25. 9 and 16, also 25. So, ding, 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 we have a match, which means we have a right angle. So yes, and if we were to give an explanation, our explanation would be that DE is perpendicular to CD through the converse of the Pythagorean theorem. Therefore, we have a tangent. All right, next one I'm just going to set up because otherwise this one problem would take the rest of the hour for me to go through, and I want to get to other problems. And I will not be giving you one this complicated on the homework anyways. So I will give you problems that are somewhere in between these levels of complicated, but not one this hard. So I'll just show how it's set up, and then we'll move on. ST is tangent to Q. Since we know it's tangent this time, we know it's right angle, and so we know C squared equals A squared plus B squared. Here's our hypotenuse. Once again, our hypotenuse is combining two different distances, a radius here and an outer piece here. So my entire hypotenuse is not R, it's not 18, it is those two put together. So if I were to write it in terms of that, it would be R plus 18, and that's what would go in for C, and that would have to get squared. I will stop because from there it gets more complicated than we're going to do. But in general, these problems are going to be using Pythagorean theorem. So be keeping an eye out for that. All right, back to the front page. where we're going to write down a couple more definitions and properties and theorems here. Here we go. Oh, that's showing some stuff for this problem that we're not doing. All right. In a circle or in congruent circles, two minor arcs are congruent if and only if. So again, I have two statements wrapped up into one. Minor arcs are congruent if and only if the corresponding chords are congruent. So again, that gives me two directions in one. Arcs are congruent if and only if the chords are congruent. That tells me if I know the arcs are congruent, if I know the arcs match, then I know the chords match. And I can go the other direction too. If I see that the chords match, then I know that the arcs match. So in this diagram, these segments that are tick marked in red, well, the tick marks mean that they match, they're congruent. So that tells me that their arcs that are traced out in blue also have to match and be the same. So the measurements of those two arcs are the same. So if the chords match, then the arcs match. If the arcs match, then the chords match. Good? Going on. This is also going to be two if-then statements wrapped into one, but I'm actually going to talk about them separately. So first one. If one chord is a perpendicular bisector to another chord, then the first chord is a diameter. So remember what some of these terms mean here. Remember, chord is just a segment on the circle. Perpendicular, right angle. Bisector splits into two equal pieces to another chord. Then the first chord is a diameter. Passes through the center. What this is really doing is it's giving us a fancy way of saying that that a diameter is going to be the only way to split a circle cleanly into two equal pieces, which we actually used in the first part of this chapter to get some angles, because sometimes we use the fact that halfway around the circle is 180 degrees, using the fact that a diameter splits our circle into two equal pieces. So if I see perpendicular bisector on a chord, then I know diameter. And then let me take it the other way. Okay. Let me take it the other way. If a diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. So this time, if I have diameter getting perpendicular to a chord, then I'm going to know bisector. So last time it was if I knew perpendicular bisector, then I knew diameter. This time I know diameter and perpendicular, and that will tell me bisector. And notice it says that it bisects the chord and its arc. And that goes back to the fact that when the chords are the same, or when the chord pieces are the same, then the arcs are the same. It's that same idea that we've already referenced and talked about. Okay, and we'll have one more on this page that we'll do tomorrow. Okay, I'll come back to it at the end of the hour. Let me do this example, and then I'll come back to it. Let's try one that uses a couple of these theorems. Find the measure of the given arc or chord. Provide your justification. Find arc B to C. So arc B to C is this piece right here. And all I know is that this piece, A to B, is 116. Well, since I know that piece is 116, let's go ahead and figure out what the rest of the circle is. Arc ACB. So the major arc, greater than 180. The major arc, the rest of the circle, should be 360 minus 116, which is 244. And from there, I want to figure out what this part of it is, B to C. Well, here comes the theorem that we're using today. How much of the 244 degrees is this? It's half of it. How do I know it's half of it? Because I have these two chords right here being the same. And we had that theorem that said if the chords were the same, then the arcs were the same. So these two arcs have to be equal. These two arcs have to be equal. So C is acting as kind of a midpoint between, and the arc between A and B. So that means if I just take the 244 and divide it by 2, split it in half, that will give me this measurement. And that is because the chords were the same, which